All right, folks, I think we're going to try to stick on the clock and get going, even though folks are still pulling themselves away from yogurt and peanuts. We have 3 more presenters this afternoon in this session. And then, of course, you know that afterwards at 5 o'clock is the social hour in the exhibit hall. I'm going to introduce quickly, or let him mainly introduce himself. But our first presenter is Corey White, PhD. From NC State University, or as I like to call him, Corey White, Warren Wilson College, class of 2010. So, thank you, Corey.
Well, just because I don't know how long I don't want to go over. We can, if you want to learn more about me, we can talk after the presentation. But welcome, thank you all for coming to my talk today. All right, so. Communities and regions that are rapidly urbanizing and experiencing an increase in extreme precipitation events are becoming increasingly more vulnerable to flooding and water quality degradation. However, communities often do not agree on what or where problems are, or if these problems even exist. These problems are known as wicked problems due to how challenging they are to address in socio-environmental planning. These problems are especially difficult to address in polycentric areas with disparate managing agencies like local government, municipalities, cross environmental boundaries like watersheds. This is because of barriers to collaboration, such as financial constraints associated with major capital infrastructure projects, lack of incentives for collaboration, and managing agencies not having the jurisdictional power to define problems and enact solutions. So participatory modeling is an approach to address wicked socio-environmental problems, where community members and other stakeholders are an essential part of the modeling process. The participatory modeling process is an iterative process that has the ability to build trust in modeling results, increase community ownership over a problem, and build a shared understanding of problems between top-down and bottom-up stakeholders. Where top-down stakeholders are members of federal or state level government creating laws and regulations, and bottom-up stakeholders are like local managers, community groups that work within these regulations presented from kind of the top-down level. So participatory modeling works by raising the level of participation in communities. For example, no participation is basically just where no communication is occurring between stakeholders. The next level of participation would be considered low participation, and this is where communication is one way, either flowing down or up. And then the highest level of participation is where you have communication flowing in both directions, and this is when you get to these higher levels of co-design and co-decision making, your stakeholders start to form a sense of ownership, or in the best case, a mandate to act as co-decision makers. So the participatory modeling process requires multiple steps of continual engagement. That includes identifying stakeholders, fact-finding, process orchestration, model conceptualization, and quantitative model development. However, no participatory modeling project is exactly alike, and they all follow a common set of methods. Today, we're going to really focus on when participatory modeling efforts are spatially explicit. So we call this process geospatial participatory modeling. So geospatial participatory modeling facilitates community engagement and knowledge co-creation by ongoing, iterative, adaptive, interactive, and equitable public engagement that enables stakeholders to connect to place by making the issue personal, uncovering how decisions at one location impacts other locations, and defining often ignored or abstracted issues surrounding spatial scale and drivers of problems, and the spatial scale of drivers and problems, the drivers of problems and data. So this is also important because top-down and bottom-up stakeholders operate at different spatial scales in the decision-making process. So when developing a geospatial participatory model, many questions must be answered to figure out what the model consists of. So some of these questions include, who are the stakeholders? What are the modeling goals? What models and data are needed? What type of scenarios need to be run? How can stakeholders interact to develop these scenarios? And what sort of feedback is needed to assess if basically these modeling goals are met? Additionally, we needed to find the appropriate spatial temporal scale for each of these modeling components. So for example, we can design a geospatial participatory model that couples regional urban growth model that forecasts future development scenarios with an environmental model simulating the impacts of forecasted development on inundation, runoff, and erosion. Stakeholders could engage with the model by parameterizing population and climate change projections, and steering the model by defining spatially explicit development policies and stormwater control measures. So in this example, stakeholders would receive feedback surrounding changes in property damage, traffic, and water quality. However, developing web-based geospatial participatory model is a difficult task to perform efficiently in practice because of the technical knowledge, cost, and time required to build ad hoc applications. So to address this issue, I developed the Geospatial Participatory Modeling platform. To develop the platform, I created 6 new open source libraries that build from 40 years of open source geospatial software and standards. So real quickly, so before discussing the platform, let's take a quick step back in GIS history to see kind of how we arrived at where we are today. So starting in the late 1980s, desktop GIS software like GrassGIS started to emerge, allowing the digital management and analysis of geospatial data. By the 90s, web mapping started to appear along with the development of supporting technologies such as map servers and geodatabases. The early 2000s was a golden era in open source GIS with the emergence of MapBender, PostGIS, GeoServer, QGIS, OpenStreetMap, and OpenLayers. This time period also harbored the first digital Earths. By the mid to late 2000s, geocomputational and 3D modeling software began appearing, allowing new applications to be developed to run geospatial analysis online, including the development of interactive 3D maps. The 2010s marked the beginning of big data computation and more advanced rendering of geospatial data in web browsers and mobile devices. By the mid-2010s, we started to see the first attempts of game engines for rendering geospatial data and the adoption of current technology trends like cloud-optimized geotiffs and spatial temporal asset catalogs. So currently, scalable data-on-demand cloud-based Earth observation platforms are leveraging advancements in distributed computing and machine learning to enable a new era of data products. Some of these data products include land use, land cover monitoring, elevation change, flood extents, and flood damage probability. So spatially explicit dynamic stochastic models like urban development and process-based physical models such as surface water flow can now use these data sets as input to model socio-environmental systems. However, while utilizing remotely sensed data as inputs to spatially explicit models is key, without a participatory component, it's usually insufficient to make decisions regarding complex socio-environmental issues. Participant engagement is necessary to address model uncertainty, build trusted model outcomes, bridge diverging opinions, educate, and improve the quality of decision-making. So to address this, a geospatial participatory model platform would need to combine the computational power of cloud computing platforms with the interactivity of online geospatial platforms in order to simulate diverse socio-environmental models to facilitate public engagement and knowledge co-creation. So I developed and submitted to the Journal of Environmental Modeling and Software an OpenPlanes. It's an open source geospatial modeling platform designed for data-on-demand, multi-model interaction, and customizable participant engagement. The goal of OpenPlanes is to increase access to geospatial participatory models by reducing the barriers to development and engagement. To achieve this goal, OpenPlanes was developed using GrassGIS and Octinia to provide developers access to 400 plus tools and 400 plus plugins, and the ability to perform distributed cloud-based modeling. OpenPlanes provides an additional layer on top of this that allows developers and modelers to include complex business logic and an interactive user interface, share models, and has a growing list of provided data sets commonly used in geospatial modeling. So OpenPlanes has 2 main user distinctions, development users and engagement users. Development users are generally part of the technical team that's researching and modeling and developing customized applications, while engagement users are model end users, such as community members, facilitators, project administrators, local managers, and decision makers. OpenPlanes handles data management using spatial temporal asset catalogs, or STAC catalogs, and cloud-optimized geotiffs, PostGIS, and third-party geoportals. Additionally, OpenPlanes provides data-on-demand access to many socio-environmental modeling datasets, such as elevation, land use, land cover, satellite imagery, population, and OpenStreetMaps. So let's look how OpenPlanes works. Starting with the point of view of a development user, project datasets can be explored through the browser for all models that the user has access to. Like other geospatial software, detailed metadata is available to give the user important information needed for modeling. And each layer, including rasters, can be interactively explored in the browser by filtering data and changing color palettes. GraphGIS tools and models are also available for the development user in the browser, so that developers can create, visualize, and share their models with other users. All right, so now that I've briefly shown you how the development side of OpenPlanes works, I'm gonna switch focus to the engagement users. Engagement users interact with what I call OpenPlanes applications. So an OpenPlanes application consists of goals, which define the purpose of the geospatial participatory model, scenarios that define the role of the participant, interactions that define how the user engages with the model, the geospatial models used by the application, and the feedback metrics that let users know if they are accomplishing the modeling goals. So I'm gonna demonstrate how engagement users now interact with two sample OpenPlanes applications, one developed for spatial temporal watershed analysis, and the other is an urban growth forecasting application. And both of these models can be used anywhere in the contiguous United States. So to support community engagement, I developed a custom OpenPlanes application to allow participants to explore the landscape evolution of land cover change of user-selected upstream contributing areas simply by clicking on the map. The application can be defined in the following ways. The goal of the application is to enable participants to explore the landscape evolution of watersheds anywhere in the continental United States. The scenario is simply to explore locations of interest to the participant. The participant does this by interacting with the application a few ways, by clicking on the map to select where they want the analysis to run, exploring different land cover definitions using the interactive legend, and viewing each year of the land cover data by sub-watershed. The application performs a watershed and spatial temporal land cover change analysis, and the feedback as a polygon of the sub-watershed, summary statistics, and a time series land cover change within it. So let's see it in action. All right, in this example, we'll explore the landscape evolution of locations. We'll explore the landscape evolution of some locations that were identified by stakeholders in the Triangle region as problem areas for stormwater management. So, what you can see here, they're filtered by the, is the screen blurry or is this just from my angle? I can't tell. Which is filtered by the extent of the map, these problem locations. So by clicking on the map at a location identified as high severity, we can explore the landscape evolution of a stakeholder-defined location. When the map is clicked and the animation is started with clouds and rains while the analysis runs, during the analysis, 30-meter elevation data and 30-meter land cover data are ingested for the years from 2001 to 2019 from the cloud for the extent of the watershed. During this process, the stream flow, stream direction is calculated for the entire watershed using the elevation model, and the user's point is snapped to the nearest stream before calculating its upstream contributing area and saving results to the database. So when the process is complete, a blue polygon is returned representing the upstream contributing area along with summary statistics and a graph representing the land cover change from 2001 to 2019. The time series can be explored as different types of graphs with colors matching the land cover type and descriptions provided in the legend on the left. The different years of land cover data can be explored for the entire watershed using the dropdown on the right. So by zooming in on another example, we can see how quickly users can identify trends in land cover change. In this example, summary statistics show the upstream contributing area was 45.3 square kilometers with a mean elevation of 103 meters. The land cover change graph indicates that between 2016 and 2019, medium intensity development increased from 7% to 19% of the watershed, and the temporal data view shows where the development occurred. So, watch it. Coming down right here. So that's all, if you know the triangle area, that's all flowing into Jordan Lake. All that's new development. So in the future, additional novel metrics of landscape evolution are under development to be added to continue to explore the impacts of landscape evolution. For the next demonstration, I developed an open plans application to enable stakeholders to simulate urban growth scenarios with hypothetical land use policies. In this example, the goal of the application was to enable participants to engage in the co-development of regional urban growth scenarios over time. To achieve this goal, participants will develop hypothetical land use policies to promote or restrict development. They'll do this by drawing polygons on the map to indicate their desired development outcome, providing input to an urban growth model that provides feedback about the cost of intervention, decision outcomes, projected development. So the application was developed so that the communities can engage with the future urban regional environment simulation, or futures, in just a few steps. So to begin, an administrator needs to create a new modeling environment for their desired region. Futures can be run efficiently over large spatial extents. So the administrator is allowed to select up to 5 connected counties. The administrator must also provide details for the modeling environment, such as the name and description, because the futures model is parameterized to allow the development of different urban growth scenarios as hypothetical land use policies. The administrator can set predefined goals, such as protecting natural resources or limiting landscape fragmentation. Once the administrator is complete, they submit their model. So after the user model is submitted, an initial process is started that ingests all this data that's required for modeling. This includes elevation, land cover, transportation, population, and protected areas. During this process, input features such as development pressure are also calculated, and the status quo scenario is run. So once the model has completed initializing, it's ready for the participants to begin developing their own development scenarios, utilizing the predefined budget. The user can then develop their own policy by drawing polygons on the map where they'd like to modify the development potential. The budget is updated to reflect the cost of the land, and the user may continue until the budget is spent or they choose to stop. So once the user has defined the scenario, they can run the scenario and moving on to the next time step in the model, updating the forecasted development patterns. So the scenarios can be aggregated and analyzed based on modeling feedback and goals in addition to the general usage data. So in this example, you can see how many active users you have, the number of run scenarios, the average cost of interventions, projected development, and it could also shows different scenario outcomes based on if you change what you're doing at different time steps during the forecasting. In the future, aggregated data views of all participants could also be provided to identify spatial patterns of where participants are in agreement or disagreement about spatially explicit development outcomes. So in the future, coupling these development scenarios with flood risk models may be used to provide further information regarding damage to buildings, changes to traffic patterns, and the impacts on water quality. So these are just a few examples of how open plans can be used to develop web-based interactive geospatial participatory models. However, Open Plains is not a replacement for the participatory process. Rather, it's a platform that aims to raise the level of civic engagement. And it does this by removing barriers to geospatial participatory modeling and to address wicked socio-environmental problems. To effectively address wicked socio-environmental problems, stakeholder engagement is an essential part of the decision-making process. Through the participatory process, you can engage with stakeholders to define problems, build a shared understanding of the system, in many cases, a spatial component, and in many cases, there's a spatial component to the system that needs to be addressed through geospatial participatory modeling because making it spatial makes it personal. And so this is all available on GitHub and it's all open source. But I also plan on just hosting a public version online so people can explore and try it out themselves. So, anybody, any questions? Sorry if I was over, David.
So, if you run this locally, I think not. You need a server and then it's interactive web map.
Yeah, so you could run it locally depending on how powerful your computer is and the type of model you're running. But yeah, it's designed to be run online.
And so, are you then, would I need to host an LCD stacks of raster data as well, or can you do it in existing servers?
So right now, I am, until it becomes, if there's enough traction where I can't afford it, it's all provided. There's other services like Google Earth Engine and Microsoft Planetary Computer and all these other groups that you can get tokens to and ingest their data directly from there. It was an intentional design decision not to do that at this point by trying I didn't want friction and I didn't want to push people into any one platform. So but knowing that if a lot of people started using this, that would get expensive. So it's probably not a forever solution, but it's the current solution.
Kind of simple nuts and bolts question, and maybe I didn't understand totally here, but it looked like you had the user had the ability to define a watershed for a certain point, right?
Mm-hmm.
How do you do saints and cohorts in certain areas?
So for this demonstration, I'm using 30-meter elevation data. It kind of gets filtered out, but then also the algorithm that's getting used doesn't. It's not one where you need to fill the DEM beforehand. It has a path finding algorithm, so it's able to go into these dips and come out and keep on moving. Yeah.
All right, thank you again, Lori.
Thank you.